Right now, without moving, without looking up, without doing a single thing, you are hurtling through space at 514,000 miles per hour. That's how fast our solar system is orbiting the center of the Milky Way. You've never felt it. You've never noticed it. And yet, it is happening to you right now as you watch this. The thing we are orbiting, the thing every human civilization has built their calendars, religions, and entire understanding of time around, is a star. Our star, the Sun, and by cosmic standards, it is embarrassingly average. There are stars so large they would swallow Jupiter's orbit whole. Stars so dense a teaspoon of their material weighs 1 billion tons. Stars that pulse like a heartbeat so precise they were once mistaken for alien signals. And when you look at the night sky, some of what you see isn't even the present. It's light from stars that died millions of years ago, still crossing the void, still reaching your eyes. You are looking at ghosts. Today we're reading every single one of them. Every type of star, how they live, how they die, and what they leave behind. By the end of this video, you will never look up the same way again. Let's start with the most common star in the universe. Not the most dramatic, not the most powerful, but the most everywhere. Red dwarfs make up approximately 70% of all stars in the Milky Way. For every sun-like star you can imagine, there are roughly 3 red dwarfs hiding in the dark nearby. Too dim to see with the naked eye, too small to dominate, but absolutely relentless in their existence. And when we say small, we mean it. The largest red dwarfs are about half the mass of our sun. The smallest are barely above the threshold of being a star at all, teetering on the edge between star and planet-sized object called a brown dwarf. They burn cool and red, surface temperatures hovering between 2,000 and 4,000 Kelvin compared to our sun's 5,500. But here is where the red dwarf becomes genuinely fascinating. They are almost impossible to kill. Our sun will live for about 10 billion years total. It's currently halfway through that lifespan. Red dwarfs? The smallest ones are calculated to burn for up to 10 trillion years. That is 1,000 times longer than our sun. It is so incomprehensibly longer than our sun that the universe itself, currently 13.8 billion years old, has not yet been around long enough for a single red dwarf to die of old age. Not one, in the entire history of the universe, has died. They just keep burning. Slowly, quietly, indefinitely. Now, here's where it gets complicated. Red dwarfs are also the most promising candidates for hosting habitable planets. They're the most common star, they live the longest, and several confirmed exoplanets in habitable zones have been found orbiting them, including Proxima Centauri b, orbiting the closest star to our own sun. But there's a catch. Red dwarfs are violent in their youth. They produce intense solar flares, bursts of radiation powerful enough to strip the atmospheres from nearby planets. And because a habitable zone planet around a red dwarf must orbit extremely close to stay warm, those planets are sitting directly in the firing line. So the most common star in the universe, the longest living, the most abundant, might also be one of the most hostile to the kind of life we're looking for. The universe, as always, gives with one hand and takes with the other. You already know this one. You've known it your entire life. You've felt it on your skin, grown food with it, measured your days by it. The yellow dwarf is the most personally familiar object in the entire universe, and somehow, still one of the most underappreciated. Our sun is a yellow dwarf, technically classified as a G-type main sequence star. Surface temperature around 5,500 Kelvin, mass roughly 330,000 times that of Earth, diameter wide enough to fit 1.3 million Earths inside it. It converts 600 million tons of hydrogen into helium every single second through nuclear fusion, and has been doing so for 4.6 billion years without interruption. Not once has it missed a day. Yellow dwarfs sit in the sweet spot of the stellar classification chart. Not too hot, not too cool, not too massive, not too small. They burn stable and steady for around 10 billion years, long enough for complex life to develop, evolve, build civilizations, and look back up at the sky and start asking questions. That stability is everything. Life on Earth didn't happen because Earth is special. Life on Earth happened because the sun is boring, predictable, consistent. It doesn't randomly flare and irradiate everything. It doesn't burn out in a million years before evolution gets started. It just shows up, every day, for billions of years. And that relentless, unremarkable consistency is the single most important factor in the existence of every living thing you have ever encountered. Boring saved your life, repeatedly, for 3.8 billion years. But yellow dwarfs don't last forever. In about 5 billion years, our sun will exhaust its hydrogen fuel. And when that happens, the stability ends. The core will contract, the outer layers will expand, and the sun will swell into something unrecognizable. A red giant, large enough to engulf the inner planets. The same star that quietly nurtured life for billions of years will end by consuming the world it created. But that's 5 billion years away. For now, it rises every morning, it sets every evening. And somewhere in the cosmos, around other yellow dwarfs just like ours, the same slow, patient process that produced us might be happening again. Right now, on worlds we haven't yet found. If the red dwarf is a slow burn and the yellow dwarf is a steady flame, the blue giant is an explosion that never stops happening. Blue giants are the rock stars of the stellar world. Massive, blindingly bright, burning at surface temperatures between 10,000 and 30,000 Kelvin. So hot that they emit most of their light in the ultraviolet spectrum, beyond what human eyes can even detect. The visible light they do produce is a fierce, electric blue-white that outshines our sun by tens of thousands of times. They are extraordinary, and they pay for it. Where our sun burns for 10 billion years, a blue giant burns through its fuel in 10 to 100 million years. In cosmic terms, that is nothing. That is a match struck and extinguished before the universe has had time to blink. They live fast, burn violently, and die young. And the deaths they die are among the most catastrophic events in the universe. But while they're alive, they reshape everything around them. The radiation pouring off a blue giant is so intense it carves cavities in surrounding nebulae, sculpts the formation of nearby stars, and ionizes entire clouds of gas across hundreds of light years. They don't just exist in their environment, they dominate it. They bully it. They restructure it according to their own violent agenda. Rigel, the bright blue star in the constellation Orion, is a blue giant. It sits approximately 860 light-years from Earth and is roughly 120,000 times more luminous than our sun. When you look at Orion on a clear night and find that brilliant blue-white point of light at the bottom right, that is a star so powerful it would sterilize our entire solar system if placed where the sun sits. And it will be dead in a cosmically short time, already in the final stages of its life, already burning through its last reserves. Blue giants don't fade quietly. When they exhaust their fuel, they collapse and detonate in a supernova, one of the most energetic events in the known universe. For a brief period, a single exploding blue giant can outshine an entire galaxy of 200 billion stars. One star, brighter than 200 billion. Extraordinary, violent, gone too soon. The blue giant burns like it knows it won't last, and it makes absolutely certain that everyone notices. Everything we've discussed so far has been building to this. If you want to understand the sheer, almost offensive scale of what the universe is capable of producing, you need to meet the red supergiant, the largest type of star by volume that we know of. Objects so incomprehensibly enormous that the word big fails completely as a descriptor. Betelgeuse. You've likely heard the name. It sits in the constellation Orion, the bright reddish-orange star at the upper left shoulder of the Hunter. It looks like a modest point of light from Earth, 700 light-years away. But if you replaced our sun with Betelgeuse, its surface would extend past the orbit of Jupiter. Not Earth, not Mars, Jupiter. Everything in our inner solar system, Mercury, Venus, Earth, Mars, the asteroid belt, would be inside the star. And Betelgeuse isn't even the largest red supergiant we've found. UY Scuti, VY Canis Majoris, Stephenson 2, 18. These are stars with radii so large that light, traveling at 186,000 miles per second, would take hours to travel from one side to the other. Our sun is a marble next to these objects. But size comes at a cost. Red supergiants are dying stars. They are what massive stars become in their final stages: bloated, cool, and unstable. Their surface temperatures are relatively low for a star, between 3,500 and 4,500 Kelvin, which gives them that distinctive deep red-orange color. But internally, they are catastrophically unstable. Their cores are burning through increasingly heavy elements in a last desperate attempt to maintain the pressure that keeps them from collapsing. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. And when they reach iron, it's over. Iron cannot be fused to release energy. The moment an iron core forms, the fusion stops. The pressure holding the star up vanishes in less than a second, and the entire mass of a star larger than Jupiter's orbit collapses inward at a quarter of the speed of light. The resulting explosion, a Type II supernova, releases more energy in a fraction of a second than our sun will produce in its entire 10 billion year lifetime. Betelgeuse is already in this final phase. Astronomers have been watching it pulsate and dim unpredictably. When it goes, and it will go, possibly within the next 100,000 years, possibly tomorrow, it will be visible in our daytime sky, bright enough to cast shadows at night. The largest stars in the universe don't retire, they detonate. Now we slow down. We go quiet. After the violence of supergiants and the intensity of blue giants, the white dwarf represents something different entirely. It represents the end, not the explosive, catastrophic end of a massive star, but the long, slow, dignified decline of a star like our sun. When a mid-sized star like our sun exhausts its hydrogen fuel, it swells into a red giant, expanding outward, engulfing its inner planets, burning through its outer layers. Then, over thousands of years, those outer layers drift away into space as a planetary nebula, one of the most visually stunning phenomena in the universe, a glowing shell of expelled gas surrounding a collapsed stellar core. What remains at the center is a white dwarf, roughly the size of Earth, containing roughly the mass of the Sun. Let that sit for a moment. The mass of the Sun compressed into a sphere the size of our planet. The density is almost incomprehensible. A teaspoon of white dwarf material weighs approximately 15 tons. White dwarfs no longer fuse anything. They produce no new energy. They are simply radiating away the heat they accumulated over billions of years of fusion. Slowly, steadily, cooling into the dark. They are stellar embers, and they cool extremely slowly. The universe is not yet old enough for a single white dwarf to have cooled completely. Every white dwarf that has ever formed, from the very first stars that died in the early universe, is still glowing, still warm, still visible. But eventually, over trillions of years, they will cool completely. The glow will fade, the ember will go dark, and what remains is something theorized but never yet observed: a black dwarf, a cold, dark, inert sphere of crystallized carbon and oxygen, drifting silently through a universe so old it barely resembles the one we know. Our sun will become a white dwarf. In approximately 5 billion years, what remains of the most important object in human history will be a cooling ember the size of Earth, floating alone in the dark, quietly fading. For trillions of years, there is something unexpectedly moving about that. If the white dwarf is a quiet ending, the neutron star is something else entirely, something that shouldn't exist, something that sits right at the edge of what matter is even capable of being. When a massive star, larger than our sun but not quite large enough to form a black hole, reaches the end of its life and detonates in a supernova, the core that remains behind is compressed beyond anything a white dwarf experiences. Protons and electrons are forced together under gravity so intense that they merge, forming neutrons. The entire core collapses into a sphere of pure neutron matter roughly 12 to 15 miles across. 12 to 15 miles across. That is smaller than most cities, and it contains more mass than our sun. A teaspoon of neutron star material weighs approximately 4 billion tons. The surface gravity is 200 billion times stronger than Earth's. If you somehow survived being transported to the surface of a neutron star, which you wouldn't, not even close, you would be instantly compressed into a layer thinner than an atom. But the physics gets stranger. Neutron stars spin, and they spin fast. When the massive stellar core collapses, conservation of angular momentum causes it to spin faster, the same way a figure skater pulls their arms in and accelerates. Newly formed neutron stars can complete hundreds of rotations per second. Some have been recorded spinning at 716 times per second. As they spin, they emit beams of electromagnetic radiation from their magnetic poles. If those beams happen to sweep past Earth with each rotation, like a cosmic lighthouse, we detect a precise rhythmic pulse of radio waves. We call these objects pulsars. When pulsars were first discovered in 1967 by astronomer Jocelyn Bell Burnell, the signal was so regular, so precise, so unlike anything natural previously observed, that the research team briefly considered whether it might be an artificial signal from an extraterrestrial civilization. They called it LGM-1, Little Green Men. It wasn't, but the fact that a natural object in the universe produces signals precise enough to be mistaken for alien communication tells you everything you need to know about how extraordinary neutron stars are. At the extreme end of neutron star behavior sits the magnetar, a neutron star with a magnetic field so powerful it represents the strongest known magnetic field in the universe. A magnetar 1,000 light-years from Earth, releasing a single burst of energy. would strip our atmosphere. There is one in our galaxy, SGR 180620. It sits 50,000 light-years away. That distance is the only reason we're here to talk about it. We've talked about big, now we talk about incomprehensible. Hypergiants are the most massive stars in the known universe. Not just large by stellar standards, large by any standard. Objects that exist at the absolute theoretical limit of how massive a star can be before its own radiation pressure tears it apart are 136A1, currently the most massive known star, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Mass estimated at 180 to 200 times that of our Sun. Luminosity approximately 4.6 million times greater than our Sun. If you replaced our Sun with R136A1, its radiation pressure alone would blow away the atmospheres of every planet in our solar system within years. Hypergiants are so luminous that they are visually observable from other galaxies with the naked eye. Individual stars, visible across millions of light-years of space. But they are extraordinarily rare and extraordinarily short-lived. Their immense mass means they burn through fuel at a catastrophic rate. Where our Sun lives for 10 billion years, a hypergiant may live for just 1 to 3 million years. In galactic terms, they are born and die almost instantaneously, and their deaths are the most violent events a single star can produce. Hypernovae. Explosions so powerful they dwarf standard supernovae, releasing gamma-ray bursts that can be detected from billions of light-years away. The most energetic explosions in the universe since the Big Bang itself. One hypernova, one gamma-ray burst, pointed at Earth from within our galaxy. Game over for the biosphere. No warning, no survival, just the most powerful beam of energy in the universe, arriving at the speed of light. There are no known hypergiants close enough to threaten Earth, currently. Every star we've discussed so far has been defined by what it is. Variable stars are defined by what they do. They pulse, they breathe, they expand and contract on rhythms so precise and so reliable that astronomers use them as cosmic rulers, measuring the distances to other galaxies with them. A variable star is any star that changes in brightness over time. Some do it because they physically pulsate, their outer layers expanding and contracting in a regular cycle driven by internal pressure changes. Others do it because they are part of binary systems and periodically eclipse each other as seen from Earth. The most important class of variable stars are Cepheid variables, named after Delta Cephei, the first of its kind to be studied. These are giant stars that pulsate with a period directly related to their luminosity. The longer the period, the brighter the star. This relationship, discovered by astronomer Henrietta Swan-Leavitt in 1912, became one of the most powerful tools in the history of astronomy. Because if you know how bright a star truly is, and you know how bright it appears from Earth, you can calculate exactly how far away it is. Cepheid variables became the first reliable method for measuring distances beyond our own galaxy. It was Cepheid variables that allowed Edwin Hubble to prove, in 1923, that the Andromeda Nebula was not a cloud of gas inside the Milky Way, but an entirely separate galaxy, millions of light-years away. That discovery didn't just expand our map of the universe, it revealed that the universe was incomprehensibly larger than anyone had imagined. The entire modern understanding of cosmic scale, the billions of galaxies, the expanding universe, the Big Bang itself, traces back to a pulsating star and a woman who noticed a pattern in its rhythm that nobody else had thought to look for. Variable stars don't just change brightness, they changed everything. 8 types of stars. 8 completely different expressions of the same basic process: hydrogen, gravity, nuclear fusion, time. From the red dwarf burning quietly for 10 trillion years to the hypergiant that detonates in 3 million. From the steady, reliable yellow dwarf that made your existence possible to the neutron star spinning 716 times a second in the dark. From the white dwarf cooling alone for trillions of years to the variable star that rewrote our understanding of the entire universe. Every point of light in the night sky is one of these, a story in progress. A life cycle measured not in years, but in billions of years. A process so vast and so ancient that the light reaching your eyes right now may have left its source before your solar system existed. And here is the thing that stays with me. Every atom of carbon in your body, every atom of oxygen in your lungs, every atom of iron in your blood, was forged inside a star. Not a star like a metaphor, not a star like a poetic idea, an actual star, a collapsing, fusing, burning ball of plasma, that lived and died billions of years ago and scattered its contents across space, and those contents drifted and clumped and eventually became you. You are not looking up at the stars. You are looking at where you came from. If you made it this far, subscribe. There's so much more to explore.